Greetings, it's Paul welcoming you to Script 2M from Math 23C, in which I plan to work through some standard elementary problems in probability involving flipping coins, rolling dice, and drawing playing cards, all by using data frames in R and counting rows. So let's start with coins. We take a fair coin, one that's equally likely to come up heads or tails, and flip it 3 times. We have to start by making a data frame for the set of 3 flips, and we can do that in exactly the same way that we were creating data frames for logical variables. We have 2 possibilities for a single flip. Either it comes up heads or tails, and we need the Cartesian product of those 3 probabilities. So I will use expand grid, store the result in a variable named coin3, and let's see what we've got. Notice I said flip 1 equals x, flip 2 equals x, and flip 3 equals x, so I actually end up with a data frame where all the columns have appropriate names, and there are 8 rows corresponding to the 8 possible outcomes of 3 consecutive coin flips. I'm going to assume that all these outcomes are equally likely, that each has probability 1/8, because that will permit me to calculate probabilities of other events just by counting rows in this data frame. Let's introduce a random variable. A random variable is just a function on the sample space, and the function I'm going to choose is the total number of heads. How do I get that? Well, coin3, my data frame, $flip1, that's the first column, is equal to h, is either true or false, but if I use it in an expression that looks for numbers, it counts as 1. So this is 1 if the first flip's ahead, 1 if the second flip's ahead, 1 is if the third flip is ahead, and the sum of those 3 values is the number of heads. I can make a table from this column. It goes through, says the possible values are 0, 1, 2, and 3. The number of rows with each of those values is respectively 1, 3, 3, and 1. If I want to convert these frequencies to probabilities, what I have to do is divide by the number of rows, which is the length of the vector for this random variable. And now I have a vector of probabilities, which I can plot. So I get a nice little bar plot showing that the probability is 1/8 for 0 heads or 3 heads, and 3/8 for 1 head or 2 head. Now I want to find the expected number of heads. The official way of doing this is take each possible value of the random variable, multiply it by the probability of that value, and sum the results. So if I take the vector of probabilities and multiply by the vector 0, 1, 2, 3, I will get the right answer. The expected number of heads is 1.5. The law of the unconscious statistician says that in a case like this, you can also get the same answer by summing over the sample space. In other words, I can just take the mean value of this random variable, the mean value of the numeric entries in the vector, and of course I also get 1.5. What would I do if the coin was unfair? Well, there's an outrageous way of dealing with this if the probability of a head is a rational number. Suppose the probability of getting a head is 3/5. What I'll do is use 3 copies of h and 2 copies of t and say each of these outcomes is equally likely. So I make my vector x by repeating h 3 times, repeating t twice, concatenating those together, and then I use expand grid again. And for my unfair coin, I now have a data frame with 25 coins, with 125 rows. If I assign a probability of 1 125th to each of these, I have the right probabilities. The probability of a head is 3/5 for each of the 3 flips. Again, I can count the number of heads, add it to the data frame. Again, I can make a table. The values are 0, 1, 2, and 3, but the number of rows with each of these values is different from what it was before because we got 3 heads for every 2 tails. I convert that to probabilities, and now when I do a bar plot, I see that the most likely outcome, because heads are more probable than tails, is to get 2 heads, multiply the probability of each outcome by the numerical value of that outcome. I discover that the average number of heads is 1.8. That's 3/5 of 3. Alternatively, I can just sum over the sample space. Take the mean of the 125 entries in this vector. The only difficulty with this approach is that it only works if the probability of a head is a rational number, and if the probability of a head is something like 8/19ths, you are going to get a very, very large data frame. Let's move from coins onto dice now. When you roll a true die, the possible outcomes are the values 1 through 6. 1:6 makes a vector with those 6 entries, as you can see. If I want to know the expected value of the roll, which I'll call mu, I just take the mean of that vector. It's 3.5, of course. But usually what people like to do is to roll a pair of dice. Let's assume we've got a red die and a green die, and now we need 2 columns. For red, what I'm going to do is repeat this vector x, but take each component of the vector and repeat it 6 times, and you can see the result, 6 1s, 6 2s, and so on. Now I want 1 through 6 to match up with each of these values, so all I have to do is repeat the vector x 6 times for the green die, and presto, I have 2 columns for my database. What you're usually interested in when you roll 2 dice is just the total roll, so I will add these 2 vectors. Red plus green is total. Plus is a vectorized operator, and so when I look at the resulting data frame, the third column for the total, if I can scroll up to look at it, is simply the sum of red and green. When you play the dice game craps, the first time the shooter rolls the dice, he or she wins if the total is either 7 or 11. This is the origin of the phrase 7-11. I can figure out which rows correspond to that by using the which function to find the indexes for all the rows where the total column either contains a 7 or an 11. And then the length of that vector is the number of rows where the total is 7 or 11. If I divide it by the number of rows in my sample space, that's the probability of winning, which turns out to be 2/9. The way I set up red and green, they are independent random variables. What makes them independent? The correct answer to that question is if I look at any event like red on the green die, 5 on the red die, and 3 on the green die, the probability of that event is the probability of getting a 5 on the red die multiplied by the probability of getting a 3 on the green die. And I can check that in the specific case of 5 on red, 3 on green. I get the same probability, 0.02777, etc. in both. Strictly speaking, to prove independence, I should do this for every possible pair of values. Probably the most important thing about independent random variables is that for them, the expectation of the product is the product of the expectations, and I can easily check that. Either I can multiply red by green and take the mean, or I can take the mean of red and multiply it by the mean of green, and I get the same value, 12.25, in both cases. It's standard here to calculate something called the covariance, where you subtract off the expected value before doing the multiplication, and in that case the result is 0 in both cases. What I have confirmed here is that these die rolls are what's called uncorrelated. That means the expectation of the product is equal to the product of the expectations, and there are situations where two variables are uncorrelated without being independent. Independent always implies uncorrelated, but the converse is not necessarily true. R has a built-in function for calculating the correlation of two random variables, that is two vectors, and when I apply it to red and green, I get 0. That strongly suggests that they're independent, but it doesn't prove it. Now let's think about sampling from this population of 36 possible outcomes of rolling two dice. Here's how I get one row out of a data frame. I specify the row index and leave a blank after the comma to indicate that I want the whole row. So you'll notice I got row 4, where red is 1, green is 4, and the total is 5. So now I'm going to get a larger sample. I will use the R function sample, saying I want a sample from a vector containing the integers 1 through 36. I want a sample of 10, and I want to do this with replacement. In other words, if I select an 8 on the first try, an 8 is also a possibility for the next try. And let's see what I get when I do that. I get a selection of row indices. I get 10 numbers, all in the range 1 through 36. It doesn't look to me as though any repeated this time, but that was still allowed. Now what I can do is to create a data frame from this sample of 10 die rolls. I can extract the first column. I get the values on the red die in my sample. And notice 6 never showed up, but 4 showed up twice. I can take the mean of these values, and I get 2.9. That's what statisticians call the sample mean. The population mean was 3.5, but when you draw a sample, the mean of your sample is not necessarily the same as the mean of your population. And an important task in doing statistics is to try to guess what the population mean is on the basis of your sample means. I can also compute a sample variance. It's smallish. Happened to be negative here, but it could have been positive. And when this covariance is close to 0, it suggests that the two random variables might be independent. Computing the correlation is a little bit better because I can compare with 0. That's actually not all that small. The expected value of this is 0, but when you draw small samples, you sometimes get quite anomalous results. So let's try with a larger sample. My computer's fast enough to extract 3,600 samples in the blink of an eye. So let me do this. And head just displays the first 6 rows in this database. Outcome 34 was the first to be sampled, then outcome 31, and so on. I can take the mean of this sample of 3,600, and no surprise, I now get something quite close to the population mean of 3.5. If I calculate the covariance by using the var function, I get something that's quite close to 0. And if I compute the correlation, I get something that's less than 0.01. General rule, from a large sample, you get good estimates of means and variance. From a small sample, you don't necessarily do that. It's not hard to add a third die. I'm doing this just in order to show you another way of using rep. This time, what I'm going to do is take the red column I've already got, but repeat each entry in it 6 times to get red outcomes for 3 dice. To get the green outcomes, I am going to do the same thing with green from my previous data frame. And to get the white outcomes, I am going to repeat the old green data frame 6 times. So let's call this data frame omega 3. I know it sounds kind of like fish oil, but omega is a name that statisticians like to use for sample spaces. And let's look at a bit of this. It's got 216 rows. They're all equally likely. It ends with 666 on the 3 dice, and it starts with 111. I can calculate the mean of the sum. That's 3 times 3.5 or 10.5. I can compute the variance of this quantity by adding together the rolls on the 3 dice, subtracting the expectation value for that, squaring it, and taking the mean of the result. That's 8.75. And I can make a table of probabilities for the outcomes by taking the frequencies of each possible outcome and dividing by 216, because each row has a probability of 1 over 216. When I do a bar plot of the results, you can see that I have successfully computed the outcome of rolling all numbers from 3 through 18 inclusive on my 3 dice. If I try to work with this bar plot, I will discover that it thinks that 3, 4, 5, and so on are character strings, not numbers. I will have to fuss with that later on. Another way of displaying these outcomes is by making a histogram. Hist applied to a vector gives you in R a histogram of the outcomes, and by saying I want breaks at all values from 2.5 to 18.5, I actually get something that looks just like my bar plot. The frequency of 3, 4, 5, etc. Now let's look at a different random variable. The random variable is the number of 6s that appear. How am I going to compute that? I'm going to take red 3 equals 6, which will count for 1, plus green 3 equals 6, which will give me 1 or 0, plus white 3 equals 6, which will give me 1 or 0. So this is strictly speaking the sum of 3 indicator functions, and I can make a table out of this showing that 125 times I get no 6s, up through 1 time I get 3 6s. There's actually a carnival game called Chuck-a-Luck where people bet on this, and a lot of people going to carnivals are foolish enough to think that since the probability of getting a 6 on 1 die is 1/6, the probability of getting a 6 on one of 3 dice is a half. In fact, that's not so. The probability that you will get 1 or more 6s is 75 plus 15 plus 1, which is just 91 out of 216. Let me look at the names in this table. The names are the character strings 0, 1, 2, and 3. And when you want to change the type of a variable, in R, you use a function that starts with as dot. So if I say as dot numeric of these names, now I get a vector with the numbers 1, 2, 3, and I can compute the expected number of 6s by taking 0, 1, 2, and 3 and multiplying by the probabilities that the frequencies that I've computed, and I discover that the expected number of 6s is 216 divided by 2, or 108. In other words, as you would have guessed, there are 108 6s scattered throughout this table. Now for a really curious result. Suppose I give you two rather strange dice. The faces on the red die have the number 1, 2, 2, 3, 3, and 4. On the green die, we've got 1, 3, 4, 5, 6, and 8. Can this substitute for a pair of standard dice? The answer is yes, and it's very easy for me to show it in R because I just apply expand grid to the two 6-component vectors for the red and green die respectively, and I get a database, a data frame with all the possible outcomes. This data frame has 36 rows in it, but it's a different data frame than the one we saw before. Notice, for example, row 32 and 33 are the same. 2 on red, 8 on green shows up twice. There's no way of getting an event like red equals 2 and green equals 2. I can, however, create as a random variable for this data space, for this data frame, sorry I keep saying that wrong, the total roll, and when I look at the total roll, I see that I get values that range from 2 up through 12. If I make a table of those, what do you know? It's exactly the same frequencies as with two standard dice. The bar plot looks exactly the same. And this is a very nice example of a standard phenomenon in probability and statistics. You have two different sample spaces, but there are random variables on those two different sample spaces that have the same probability distribution. In other words, here are two different sets of experiments, but if all you care about is the total roll, the probability of each outcome is the same in both cases. Enough with dice, let's move along to cards to finish up. Standard playing cards have ranks that go from ace to king, and suits that go from clubs through spades, and R is perfectly happy to make vectors whose entries are character strings too. Furthermore, I can represent a complete deck of cards by using expand grid to say combine all the possible ranks with all the possible suits. So there's my data frame with 62 rows. A standard problem in elementary probability is if you choose a pair of cards from a well-shuffled deck of 52 cards, and this is sampling without replacement. First I deal one card, then I deal another card from the 51 that remain. What's the probability of getting at least one ace? I can solve this problem with pencil and paper in 2 minutes. It took me more than an hour to figure out how to do it in R, but here's my solution. There's an R function called COMBN for combination, and I ask that to generate all possible 2-element subsets of the numbers 1 through 52 inclusive. This generates a list which has a large number of columns. To be precise, it has 1,326 columns. That's the number of pairs of integers ranging from 1 to 52. It's 52 times 51 divided by 2. I can extract one column from this. The first one I get is I chose the number 1, and then I chose the number of 2. Notice repetition is not allowed. I couldn't have got 1, 1. If I supply that as an argument or index to $rank, it converts 1, 2 into ace, the first rank, followed by 2, the second rank. And now I can figure out how to construct a logical variable has ace, which is true if and only if the pair has an ace in it. What I do is concatenate ace with ace. That gives me a vector with 2 aces. I ask, is this equal to the vector r I just constructed? Is equal is vectorized, so it compares the 2 strings with ace, counts the number of times it gets agreement, asks, is that greater than 0, and returns true if it is. So having an ace in there will make the sum positive. Now let me count the number of pairs that include an ace. For once, I'm actually going to have to use a loop. So I'm going to initialize a counting variable to 0, and I really should remember to do this with the proper assignment operator. So I'm going to use all values from 1 through capital N inclusive. I'm going to go through all the possible pairs, extract the rank associated with those pairs. That could include 0, 1, or 2 aces. In each case, what I will do is to evaluate the quantity has ace, and has ace is either true or false. When I add it to count, I will increase count if there's an ace in the pair, but not otherwise. And when this is all done, the result is the number of pairs that include at least one ace. 198. Ah, 2/13 of the number, 2/13 of the number of rows, you say. Right? Wrong. If I divide by the number of possible pairs, the number is a little bit less than 2/13. And if you think about it, that's perfectly reasonable. Because there's a small probability of getting 2 aces, the probability of getting 1 or more aces is a little bit less than the probability of getting an ace on one specific card multiplied by 2. I said I could do this problem with pencil and paper in 1 minute. Here's how. I say, what's the number of pairs that don't include an ace? Well, there are 48 non-aces for the first card. There are 47 non-aces for the second card. Divide by 2, and I've got the answer. And if I subtract that from the number of possible pairs, I discover that the difference is 198. That's the number of pairs that include an ace. Well, this is going on rather long, but let's move to topic 4. This is an application of the pigeonhole principle. What I'm going to try to do is find a fraction that's a very good approximation to the base of natural logarithms, e. So I compute e, that's the exponential function of 1, 2.718 and change. Now I'm going to make a vector of the first 101 multiples of e. In the lecture notes, I used the first 11 multiples of pi in exactly the same way. So this is a vector with 101 components. Here's what the start of it looks like. Now what I want to do is, in this vector, to look at the 2 digits right after the decimal point and look for repetitions. I start by multiplying by 100. Now I'm looking at the 2 digits immediately to the left of the decimal place, and I can extract those First, by using the floor function, saying keep just the integer part. Now I have converted 2.718 into the integer 271, and so on. And then I'm going to divide by 100 and keep the remainder. That's done in R by using the modulus operator, a double percent time. Now I have 101 numbers, all between 0 and 99 inclusive. The pigeonhole principle says there has to be a repetition among these. If I make a table of the values, I see in fact there are lots of repetitions. 2 shows up twice, 5 shows up twice, and so on. Now I just pick any remainder that showed up more than once. Let's use the smallest one, say 2, and I use which to figure out what gave rise to a remainder of 2. It says that's in row 7 and row 78. Those contained respectively 78 times e and 7 times e. When I subtract them, I'm going to get something that's very close to an integer. It's a little bit less than 193. I will round it up to 193. I know it's close to an integer because the 2 digits after the decimal place were identical. So I've got a good approximation to e. It's 193 divided by 71. That has the value 2.71831, which is remarkably close to 2.71828. I'm going to invite you to do the same thing with pi and find a super good approximation to pi by looking at the first 1001 multiples of pi. You wouldn't want to do that with pencil and paper, but with a computer it's easy. I can try again with a remainder of 5, which is duplicated, with 67, which is duplicated, with 95, which is duplicated, but in every case the difference is 71. When you use this procedure, you usually find the same approximation over and over again. Okay, so that takes care of some mathematical ideas from this week implemented in R. I hope you enjoy it and feel like adding to it.